So let's take our quick look at the calendar. Last class on Friday we talked about related rates. These are classical problems in calculus, and they are very challenging problems in calculus. Today we're going to change things up and talk about approximations, and then Wednesday we'll come back and do more related rates. And remember, all of the related rates homework isn't due until Friday, right? Any questions on the calendar? Okay, and just a heads up, it won't affect us, but tomorrow is Veterans Day and day classes are canceled here at GCC. So Tuesday day classes are canceled tomorrow. Okay, so let's take a look at the top of page 15. And we'll get our reader. Cameron, can you read the summary? Thank you. Levi? Okay, thank you. Haley, number 2. So our most basic functions this semester, linear functions, right? Those are the simplest functions we could think of. And so Andy will go to 3.
We can build this simpler linear calculus. Start by making our big bad function and our linear function have the same value as a single x value, x equals a. Next, we make the derivative of our big bad function and the derivative of our linear function have the same value as that same single x value of x equals a. That's it. Call this line the linear approximation or local linearization of the function at x.
Okay, so looking at number 4, there's this function, f of x is equal to the square root of 1 plus x. Not the worst function in the world, but certainly not as simple as a straight line. And so what we're going to do is we're going to try to approximate this square root function, like the graph of the square root function you guys know is this curve that normally starts at the origin and grows very slowly as you go off to the right. And so what we're going to do is we're going to draw a line. And we're going to draw the best line that we possibly can, a line that kind of hugs this curve for as long as it can. And so we're going to pick a number like x equals a, well, maybe at the origin. We're going to draw a line that hits the curve at the origin. How many lines go through the origin? Just forget this curve. How many lines go through the origin? Infinitely many lines go through the origin, right? All these different slopes all go through the origin. So we're going to pick the best one of all these lines so that it's as close to this square root of 1 plus x function as possible for as long as possible. So that's the goal. So what we're going to do first is take a look at this real quick sketch I made in GeoGebra just before class. All right, so what function is that? Sine. It looks like the sine graph, right? It starts at the origin, so that seems good. What should this first positive x-intercept be? Should be at pi, right? And that looks reasonable. How about the second positive one? Should be at 2 pi, which is like 6.28, so that seems reasonable, right? Okay, so pretty convincing that this is just the old sine function. So I'm gonna drag this drag this axis a little bit in. We're just gonna keep still looking like sine, right? No problems. Is it sine? That is not the sine graph, right? I can draw the sine graph. Now you can see the sine graph continuing to do its merry old thing out here, but look, it looks like it's directly on top of this other thing, right? And yet this other thing does this wild up forever and down forever. So let me actually show you what that sine looking imposter is. Actually, this function right here, x minus x cubed over, what's the exclamation point? Factorial, right? 3 factorial is how much? 3 times 2 times 1, so that's 6, plus x to the 5th over 5 factorial, plus minus plus. So this function goes for a while. The degree of this polynomial is 49, so it goes out to x to the 49th. But it is a polynomial, even though it does a very good sine of x impersonation. And so if you guys stick around for Calc 2 next semester, we'll spend a bunch of time talking about these kinds of things and how can we find a polynomial that looks like sine of x when polynomials shouldn't look anything like sine of x, right? And so we'll talk about this next semester, but what we're doing today is kind of a gentle introduction to that idea, is to find a polynomial that will match some clearly not polynomial function like the sine function. So let's give it a shot here. Number 4. Our function is square root of 1 plus x, and then we're going to try to find a line that is as close to that function as possible near x equals 0. So that's another important piece here. So let's suppose that we have our linear function, and we're going to call it ax plus b for a and b constants that are to be determined. So we're going to find the values of a and b that make that line look like the square root function, just like that polynomial looked like the sine function. It's not going to look very good because it's a line, but like I said, it's an intro. So here's what we're going to do. We're going to plug 0 in to the f of x. Let me do this guy over here. So f of x is this guy. And so we're going to plug 0 into both functions. So how much is L of 0? Is b, right? X is 0. So L of 0 is b. And then over here in blue, how much is f of 0? Square root of 1, which is 1. So if we want the line to pass through the same point as that square root function, how much is b? So b is 1, right, by making these two guys equal. Super. B equals 1. Okay, fair enough. And then we're going to do this other thing. So we make them agree at this point at x equals 0, and then we're going to make the derivatives agree. So we're going to take a derivative of our line, L prime of x equals. Remember, x is the only variable, even though there are 3 letters in this line equation. So what's the derivative of ax plus b? It's just a, right? Okay, harder is the derivative of our square root function. So maybe first step is some pre-calculus. How could I rewrite that square root function? 1 plus x to the half. Now that it looks like the half, I can take a derivative more easily. So go ahead and take your derivative of that function. And make sure you see there is a chain rule lurking here, even though it doesn't really contribute anything meaningful. But the derivative of the stuff in this case is 1. And so like it might have been something not 1, so you do have to be aware of it. Okay, and all right, so that's fine. So let's go ahead and plug the same 0 into both the line and the derivative. So coming over here, L prime of 0 is a, because a is a constant, and so that L prime function is just always a. And then over here we want f prime of 0. So 1/2 times 1 plus nothing to the negative 1/2. And this is really just 1 to any power is how much is 1. So the whole thing is just half. So if we're going to make the line and the original function agree in terms of their derivative, then how much is a? Is f. Okay, so our big conclusion here is that the formula for our line, our best line, started with ax plus b. What does that become in this case? Everyone see that? 1/2 x plus 1. Okay, so that's the idea. Again, is that you make the two functions agree at 0, and you make their derivatives agree at 0, and this is the best we can do. So I'm going to come back here if everybody's got what they need from the notes. And I'm going to graph our two functions. So we're going to hide some stuff here. And I'm going to stretch this guy way out this way. Okay, that's pretty good. All right, so the original function, or the line function, was L of x equals 1/2 x plus 1. Thank you. Let's fix that. 1/2 x plus 1. Okay, so there's our line. Yep, good. And then the square root function, that was called square root of 1 plus x. Okay, did you see it? Yeah, the line got darker because actually the line and the square root function look very much alike because I'm so zoomed in. So we'll zoom out and then we'll start to see what we expect. You can see the square root function there, right? I'll click on it so we can really tell which one is which. Right, so it's a little bit darker. So the square root function is below, and then they're really close to each other here, right? The line that we found and the square root function, and then the square root function is below here. Anything special about this particular line that we found? Petru? That's the tangent line, right? You made the tangent line hits at the point. We made the two things agree. And we just basically set the derivative, we found the derivative of the square root function and we made the tangent line have that right slope. So there's really nothing new here. It's just kind of a different way of thinking about things and then really taking advantage of this idea that, hey, if you zoom in a bunch, then they're really quite close to each other. Okay, good. So the activity is quite long, so see if you can motor on through and raise a flag if I can help.